I'm going to share my work on communication avoiding parallel algorithms for solving triangular systems. This work was partially done here with Torsten in this group, partially done with Edgar at UIUC, where I've spent like most of my last year. And yeah, this is what we came up with, and yeah, what I'm going to present at IPDPS. Real short rundown of what we're going to do, short introduction on basically problems, preliminaries, use cases, dig into previous works, look at existing algorithms, see where we can improve them, look at our algorithm, what we came up with, and then some results in the conclusion in the end. So the TRSM problem, in matrix form, pretty simple, Lx equals B, where L is lower triangular, B and X are dense. We don't consider sparse left-hand sides, and it's also important to note here that we have K, B and X of size n times K, where K is bigger than 1, so it's not a matrix vector problem, but in fact a matrix problem, and it's the multiple right-hand sides. Use cases are pretty widespread in dense linear algebra. It's a subroutine in various factorizations such as LU or Cholesky, and of course it's used once you have an actual decomposed matrix to solve your linear system. So overall, an interesting problem with a lot of subtle use cases, as in like the base cases for LU or something like that. Yeah, and we've seen potential in improving theoretical performance there. So this is why we tackled this problem specifically. For the execution time model that we used, it's pretty standard alpha, beta, gamma. So we say the complete runtime of an algorithm is dependent on somehow the latency S, the bandwidth W, and the flop cost F with their given with their given parameters beforehand. So the assumptions that we took is basically we did only look at leading order terms in all of these cases, leading order terms with respect to matrix size nk as well as p, because otherwise the computation would get really tedious and not reasonable to read anymore. So we dropped all the lower order terms as they are also not that reasonable, not that important. So also we focused on systems that have one send and one receive at a time. And the last thing that was kind of a big assumption is we did not put any constraints on local memory. It has some, it simplifies the problem somewhat. Let me come back to that in the end. Let me tell you where exactly we would see differences if we would consider memory, because this is definitely one of the points that we want to address sometimes later on. But for now, these are the assumptions that we had. So now let's dig into previous work. The first thing I'm going to present is 3D matrix multiplication. It's kind of important for us because our TRSM algorithm works on a very similar basis than this 3D matrix multiplication. I'm just going to present the bandwidth part here, since well, the flops are the same no matter how we lay the matrix multiplication out, and also if we do not have constraints on local memory, matrix multiplication can always be done in log p latency. So just the bandwidth here. If we have two very short dimensions and one long dimension, we basically want to broadcast the whole initial matrix L or whatever it is downwards, have these parts not move, and then do kind of these parts of calculation. So we're having a total of n squared data to be sent. If we have two very large dimensions and one short one, we want to move basically these parts around. So we're sending nk over root p data. And in the most interesting one, in the 3D case, where we have kind of a balanced input layout, we want to do a mix between. So we're broadcasting these pieces down, we're broadcasting these pieces over, leading us with matrix multiplication cost of n squared k over p to the 2/3. These bandwidth costs are somehow relevant because it's already been shown that we can do LU factorization within these bandwidth costs, which we assume to be optimal. And since LU is more difficult than TRSM, meaning there are like more dependencies, we expect also TRSM to achieve these bandwidth costs. So how we go about TRSM then? Again, initial problem Lx equals b was shown to be very easily solved recursively. We have a very simple way of parallelizing it, splitting the right-hand side into two parts, leaving us with two subproblems that are independent, easy to solve, easy to parallelize. And then we can split the thing dependently, meaning we split the left-hand side, we split horizontally here, and then we can basically solve the first problem very easily. But what we see here is the second problem requires the solution of the first problem. So we somehow get dependent resulting subproblems. This is what was presented previously. It opens up couple of questions. The main question is when do we stop the recursion and how do we handle the base case, right? Because this is kind of ambiguous here. So the problem we have with this is if we recurse too far, we have a super high latency since the critical path is along all these recursive steps, the dependent recursive steps. And this is kind of not what we want. So yeah, synchronization cost is dependent on this, obviously. So the goal is to reduce the length of this critical path by using this smart matrix inversion and multiplication to handle base cases, to handle bigger base cases than simply splitting right-hand sides and then solving it. Yeah, so this is basically how we intended to do recursive matrix multiplication. So what I want to say here is real fast, if this was our initial problem and we would just do the algorithm that was presented previously, we would recurse down until we can split the right-hand side among these number of processes, do sequential solves, and then we have like this rather lengthy critical path. If we, or like very simply said, we want to have fewer blocks along the diagonal since these are the dependent steps, and we want to solve these problems not by recursing, not by splitting vertically, but by doing matrix multiplication and inversion. This is basically how we planned on initially doing TRSM. So the inversion used for this is a recursive one, very easy. If we want to invert a triangular matrix, we can do that by just inverting the two diagonal blocks and then using two matrix multiplications to find the inverse of the dense block on the lower side. So we have these independent calls. If we recurse down, we have basically a critical path of length log p, since these two are independent. The depth determines the latency then. And so the difficult part about this is transitioning between these cases. So if we look at the first recursive level where L11 is on some set of processes, L22 is on some set of processes, we have this thing maybe on a bigger processor grid, and now we want to do these matrix multiplications and move up every level. This is kind of where it becomes difficult. It needs a lot of like smaller subcommunication, which might affect the bandwidth if done improperly. But this is basically the biggest issue of this recursive inversion. But other than that, it works like a charm. So the recursive approach for TRSM then is we do inversion, recursive inversion on these blocks here, and then we multiply with the right-hand side to get the solution, update the next piece, do this again, and then update forward and forward. after each step, we need an update on the right-hand side to get to the new solution. Again, the dependency is along the diagonal. These are like the number of base cases we need, the number of dependent calls, therefore the latency. A very easy thing to see where we can improve is all these base cases are independent of each other. We can solve them in parallel, and as I mentioned before, matrix inversion is somewhat, or like the latency of the matrix inversion is dependent on the number of processes involved. So we want to have as few processes involved as possible, since fewer recursive levels are optimal. And what we do is we do all these sets, all these inversions in parallel with distinct sets of processes, which leads to reasonable results. And what this achieves is basically a significantly lowered latency. This is the factor. Looks not too great. I mean, n over k is close to 1 in most cases, but we at least reduce the latency by p to the 2/3, which is already nice. We have bandwidth issues, though, if we just use this plain recursive algorithm, since we're rebroadcasting pieces of L. This is basically saying that in some cases we first multiply by a smaller block and then a larger block containing the smaller block. This leads to up to a factor of log p more communication in the 2 large dimensions case. In 1 and 3 large dimensions, it's no problem, but in 2 large, it's kind of suboptimal. So we don't want that. We want to get away from that. And what we did is we switched from a recursive to an iterative scheme. Let me demonstrate that here. The algorithm basically is we have the lower triangular L, the dense B. We invert the diagonal in parallel, and then we solve X by doing this multiplication. And then we do an update of the next chunk with this. So we need to broadcast this piece once, the new solution, xi. And then for the to avoid this extra communication, we delay updates on B. So we do local updates, and then we only broadcast back this small piece that we actually need to solve the next X. And then again, update here and only broadcast the small pieces. This algorithm gets around the bandwidth issues that we had previously. The second thing that is important now is we need these matrix multiplications, and they have kind of weird initial conditions, since the whole algorithm is based on like a 2D grid and splitting that properly. So we have input matrices on a 2D grid, but we still want to use 3D matrix multiplication to stay communication optimal. So this was kind of a challenging thing to do. We came up with a scheme that does a lot of grid transitions. I'm going to run you through like the basics of it more visually than like doing the in-depth stuff, but I think you'll get a good idea of how this is done. So we have this 2-dimensional grid where L is distributed on. We define a 3D grid that we want to use for communication, and then we all gather L and replicate it along the Z dimension. So you could see this as gathering L onto the top face and then broadcasting it down, but by doing one all gather, we're somewhat faster. We do the same thing for X. We gather it onto this face and broadcast it along this way. In order for that to work, we need to transpose it once. Now we have L replicated this way, X replicated this way, so we can do local computation, and then we basically reduce scatter in this dimension, replication in this dimension, and then another transpose to fit it back onto the 2-dimensional grid. So all this is basically just to achieve the same costs in matrix multiplication as was previously mentioned, while still maintaining these initial conditions to be 2-dimensional. If we put all these pieces together, these are final results. If we have a one-dimensional case, we just invert the whole thing, broadcast it down. You see we stay within the n-squared bandwidth, n-squared words of bandwidth. We use log squared p latency, but that is not an issue since latency is never the problem in the 1D case. Compared to like the standard method, which is the just recursive calls. This is due to the fact that we need log squared p to do inversion in log p steps, and each inversion calls a matrix multiplication again log p. But other than that, we're well within the bounds that were previously stated. The two large dimensions case is more interesting, smaller right-hand sides. You see we gain this log p factor that was previously an issue in bandwidth. Also, we could significantly improve the latency here. And the three large dimensions case, where we have few blocks along the diagonal that we invert and then multiply. You see again, bandwidth stays the same, flop costs stay the same, and latency decreases significantly. This is what the final algorithm looks like in theory. So what we did is we improved the latency by this factor nk to the 1/6 over p to the 2/3 in 2 and 3 large dimensions. We improved the bandwidth by a factor of log p, and we kind of showed this new use case for blocked inversions and matrix multiplications in dense linear algebra by solving this TRSM problem. Theoretically, we showed the benefits of this method. It's cool to see that the latency actually decreased significantly, and this will be a thing to use probably. The further work, the biggest point obviously is implementation. Currently working on that. We should be going into testing this week to actually have results, but that's not what the paper was about, so I'm not going to talk about it now. And another thing that is important, as I mentioned in the beginning, is memory. From what we've seen so far, memory should only affect the matrix multiplication cost, not any of the other parts. So we're most likely looking at gaining some latency there, or losing some latency there. But since we're pretty flexible in terms of tuning how far to recur, how to use our base cases, we should actually be able to not change the final result if we consider memory, if it's like within reasonable bounds. Of course, if memory is super tiny, there will be issues, but it seems like there are small factors coming in, and it shouldn't affect the overall performance too much. And this is it. If there are any questions to any of these things, I'm happy to answer, and thank you.